Welcome back, everybody. Today, we're going to be looking into something that's called network optimization models.
Mm,
Now, you might think networks, you're probably thinking like social media,
yeah, Facebook, Instagram.
that kind of thing. But
Yeah,
this goes way beyond that.
way beyond.
We're talking about optimizing how things move,
Yeah,
and not just like products in a supply chain. We're also talking about like money
okay,
and financial markets.
that's right.
It's pretty intense stuff.
Yeah, you can imagine any system where you're moving something efficiently from point A to point B.
Right.
That's where this network optimization comes in.
Okay.
And today we'll be specifically focusing on Federico Rica's lecture on applying this to financial optimization
Okay.
and asset management.
So where do we even begin with something like that?
It all starts with something called the minimum cost flow model,
Okay.
or MCF for short.
MCF?
Yeah, think of it this way. You're a company with multiple factories producing goods, and you need to get these goods to various stores across the country,
Mm-hmm.
each with a specific demand.
Okay.
The goal is to get every store exactly what it needs while keeping those shipping costs as low as possible.
So it's like a giant logistical puzzle.
Exactly.
Okay, you've got these starting points,
Uh-huh.
and then you've got destinations.
Yep.
And you're trying to find the most cost-effective routes to connect them.
It is. And that's where this MCF model will give us a framework
Okay.
to break this complex problem into manageable parts.
Okay.
Imagine the MCF model as a network.
Okay.
Kind of like a map. Instead of cities, we have nodes,
Uh-huh.
which can represent things like factories,
Right.
warehouses, or store locations.
Okay, got it. So these nodes are like our key points
Exactly.
in our network.
Yes.
What about the routes that connect them?
Those are our arcs.
Arcs.
Think of them like the highways or railways connecting these factories to warehouses and then onto the stores.
Okay.
Each arc has a cost associated with it, representing the expense of moving one unit of goods along that route.
Like transportation fees.
Yes, transportation fees, fuel costs, things like that.
So we're not just talking about the shortest route.
Right.
We're talking about
It has to factor in the cost.
the cost of each route.
Yes.
This sounds like we need some math to figure this out.
And that's where linear programming,
Okay.
or LP, comes in.
LP.
It's a mathematical technique that allows us to translate this real-world problem into a language computers can understand and solve.
So LP is like our translator.
Yes,
It's bridging the gap between the real physical world.
exactly. Bridging the gap between the physical world of goods and routes and the digital world of algorithms.
Okay, but how does that actually work?
So within LP, we define what's called an objective function.
Okay.
In this case, our objective is very clear:
Okay.
to minimize the total cost of transporting these goods.
So we're basically telling the computer, hey,
Yes,
find the cheapest way to get all this stuff to where it needs to go.
precisely.
Yeah.
But it's not just about minimizing cost. We also need to make sure we meet all the demands of our stores
Uh-huh.
and stay within the limitations of our network.
So it's like we're also giving a set of rules to follow
Exactly.
a logistical playbook.
Exactly. These are called constraints.
Constraint.
So, for example,
Okay.
we might have a constraint that says each store must receive a minimum quantity of goods.
Right.
Or another constraint could be a limit on the capacity of a particular route,
Uh-huh.
so we're not overloading a truck or a warehouse.
So it's about finding that sweet spot, the most
Yes.
cost-effective solution.
Yeah.
That also meets all the demands,
Correct.
but stays within the boundaries of our network.
Exactly.
Now, Federica Rica's lecture dives into some real-world applications of this, right?
She does, and one of the most compelling examples is the energy transportation problem.
Okay.
Imagine you have 3 power plants generating electricity.
Okay.
These are our origin nodes,
Right.
and 4 cities with varying energy demands
Oh, yeah.
serving as our destination nodes.
Okay.
In this case, the goods we're moving are units of energy.
So instead of trucks and warehouses, we're dealing with power lines and substations.
Exactly.
But it's the same idea.
Same idea.
Find the most efficient way to move energy from power plants to cities.
Exactly. And to make things even more interesting,
Okay.
Federico Rica provides some specific numbers for us to work with.
Numbers.
Yeah. Each power plant has a specific supply capacity:
Okay.
35, 50, and 40 units of energy, respectively.
Okay.
And each city has its own unique demand: 45, 20, 30, and 30 units.
So each piece of the puzzle has its own limitations and its
Yeah.
own requirements.
Yeah.
But what happens if things are a little uneven?
Okay.
What if, like, a power plant produces more energy than is needed,
Okay.
or a city experiences a drop in demand?
That's where things get really clever. We introduce what's called a fictitious node.
A fictitious no?
The fictitious node, it's basically an imaginary destination.
Whoa, 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 hold on. We're like bending the rules of reality here.
We are, in a way, but it's a brilliant mathematical trick.
Okay.
Let's say our total energy supply exceeds the total demand
Okay.
from the cities.
Uh-huh.
We create this imaginary destination, a fifth city, if you will,
Right.
with the demand equal to that excess supply.
So we're like creating an energy sink
Yes,
to absorb the surplus and like keep our model balanced.
precisely. And here's why it's so crucial. It ensures that all our transportation constraints remain active in finding the optimal solution.
Because if we have more supply than demand,
Yeah.
the model might just say,
It might just ignore it,
yeah.
and it might not actually be the most efficient.
Right. It'd be like having a team of delivery trucks and only using half of them because you don't have enough packages.
Exactly.
That doesn't make sense.
By introducing this fictitious node, we force the model to consider all the routes and resources, even when there's a surplus.
To make sure we're getting the most out of the system.
We're squeezing every bit of efficiency out of that system.
That's a cool trick.
Right.
It's amazing how these abstract mathematical concepts can be applied to real-world problems.
It is. And she doesn't stop there.
Oh, there's more.
There's more.
Okay.
She also talks of the shortest path problem.
Shortest path.
Yeah, and this one will take us on a little visual journey.
Okay.
Imagine you're a tourist in Pisa,
I love Pisa.
trying to navigate all the winding streets and charming piazzas.
I can hear the church bells.
Now picture all those streets and landmarks as our nodes,
Okay.
and the connections between them as our arcs.
So we're moving tourists
They're moving tourists.
instead of goods or energy.
Yes, it's like a real-life connect-the-dots game.
I love connect the
Our
dots.
origin node might be the train station.
Okay.
Our destination is, of course, the Leaning Tower of Pisa,
Of course.
and the shortest path problem uses the same MCF framework. But now our objective function shifts to minimizing the total distance traveled.
So like a built-in tour guide.
Exactly.
Okay, it's guiding us through the city the most efficient way possible.
Yes.
But wouldn't the shortest path always just be a straight line?
That's a great point. The model doesn't just consider Euclidean distance, it factors in the actual pathways available.
Okay.
So imagine our map of Pisa, with all the streets and walkways represented as arcs, each with its own distance.
Okay.
And the shortest path problem will sift through all these possible routes, taking into account the actual distances of each segment to find that most efficient way to reach the Leaning Tower from our starting point.
So we're not finding the shortest distance on a map, we're finding the shortest feasible path.
Exactly.
That takes into account the way the city's actually laid out.
Right.
But if we're talking about walking tours,
Yes.
we don't want something that's too long
No.
or too complicated.
And that's the beauty of these models, their flexibility.
Okay.
We can add more constraints to reflect those real-world considerations.
Okay.
For instance, we could set upper limits on the distance of each arc,
Yeah.
making sure our route doesn't send tourists on a marathon trek across the city.
So we're finding the shortest feasible path,
Exactly.
one that makes sense for a walking tour.
It has to make sense for a human.
Now, there's one thing that I'm still kind of curious about.
Okay.
You mentioned that theorem
Right.
about an integer solution.
Yes.
How does that play into the shortest path problem?
So remember that theorem states that if all our input data is integer or whole numbers,
Okay.
then our solution will also be in whole numbers in the context of our walking tour.
Yeah.
This means we won't have a solution that says walk half a street
Right.
or use a fraction of a bridge.
No cutting through buildings.
No cutting through buildings.
No teleporting.
No teleporting.
The solution will always use complete arcs representing the pathways in the city.
That's right.
But why is that theorem so important?
It's important because it guarantees our solutions are realistic and actionable in the real world.
Because what if the model said,
Yeah, what if it said walk 0.75 of a street or use half of a bridge?
yeah, that would be like an old video game where you can walk through walls?
Yeah, or teleport across the map.
Fun for a video game.
Yeah.
Not very helpful.
No, not at all.
So this keeps the models grounded
It
in
does.
their reality.
It's a really cool connection
Yes.
between the mathematical theory
Mm.
and the practical applications.
We're using these abstract concepts like linear programming and network flows
Right.
to solve very real-world problems,
Yeah.
from optimizing energy to guiding tourists through cities.
It's like a secret decoder ring that's unlocking these hidden patterns
Yeah.
and efficiencies
Yeah.
within these complex systems.
Yes, very complex systems.
But with all this talk about optimization
Yeah.
and efficiency, Are there any downsides
A good question.
or ethical considerations that we should be thinking about?
That is an important question.
Because these models are only getting more sophisticated.
And they're being used in more and more parts of our lives.
Yeah, you're right.
So before we jump into that,
Right.
let's dive a little deeper
I
into how these models work in practice.
Sound good.
Let's revisit that energy transportation problem,
Okay.
and we can apply the MCF model to those numbers
To those specific numbers.
that Federica Rica gave us.
Perfect.
Let's break it down step by step
Yeah.
and see how this optimization magic works.
Okay.
Okay, so let's get back to those power plants in the cities.
Right.
We've got 3 power plants
Right.
with supplies of 35, 50, and 40 units of energy.
Yes.
And we've got 4 cities needing 45, 20, 30, and 30.
Okay.
How does the MCF model actually deal with this?
It's like a giant Sudoku puzzle.
Really?
Each power plant has limited supply, each city has specific needs, and the costs of transporting energy between them vary.
Right.
The model systematically considers all those combinations of routes and flows to find the solution with the lowest overall cost.
So it's like crunching all the numbers, comparing different scenarios to find the best one.
To find the most efficient.
Can you give me like a concrete example of how this might work?
Let's imagine power plant A, with its supply of 35 units,
Okay.
is really close to City 1, which needs 45 units.
Okay.
The cost of sending energy along that route might be low because it's a short distance.
Uh-huh.
So the model might prioritize sending as much energy as possible
Okay.
from power plant A to City 1.
Makes sense, keep the transportation costs down.
Yes.
But what about City 1's remaining needs?
Right. So that's where the model gets clever.
Okay.
It might look at power plant B, which has a larger supply, 50 units,
Okay.
and calculate the cost of sending the remaining 10 units to City 1.
Uh-huh.
Now maybe power plant B is farther away, so that cost is a little bit higher.
So it's weighing the cost of each route
Yeah.
against the supply and demand.
It's a strategic game of resource allocation.
Okay.
The model might decide to send a portion of power plant B's energy to City 2,
Okay.
which needs 20, and so on.
Right. It's meticulously mapping out the most cost-effective way.
It sounds pretty complex.
It is, but that's the beauty of linear programming.
Okay.
It handles all the heavy lifting for us.
It's sifting through all these possibilities.
Finding that needle in a haystack.
That optimal solution.
Optimal solution.
So it's finding the cheapest way to keep the lights on.
It is.
But let's go back to that fictitious node.
Okay.
We've got a total supply of 125 units of energy
Right.
from our power plants.
Uh-huh.
But what happens if the cities only need, say, 110?
That's when our imaginary city
Our imaginary city.
comes into play. We create a fictitious destination node with a demand of 15 units.
15.
Exactly, matching that excess supply.
So we're telling the model, hey,
Yes.
there's extra energy, send it over here.
That's right.
But why do we even bother doing that?
Because, remember, the model's goal is to find that absolute most cost-effective solution and to make sure we use all our constraints.
So if we ignore the extra energy,
Yeah.
we might be missing something. We could miss out on a better solution.
Right. It might be cheaper to use all the power plants, even if we have a little extra.
It might lead to a more balanced distribution network.
Yeah. Okay.
Maybe less strain on the power lines
Okay.
or less energy lost.
It's about optimizing the whole system,
The entire system, not just the parts.
not just the individual parts.
Right.
Okay. I want to shift gears a little bit
Okay.
and go back to the shortest path problem.
Right.
We talked about the tourists
Uh-huh.
navigating Pisa,
Yeah.
but how do those integrality constraints actually make sure that they don't end up walking through walls?
Okay, so remember, integrality constraints force our solutions to be whole numbers.
Okay.
In the context of this walking tour,
Uh-huh.
this means we can't have a solution that says walk half a street
Right.
or use a fraction of a bridge.
Right. So it keeps things realistic.
It grounds the model in reality, making sure those solutions align with the physical constraints.
That's like a sanity check,
It is.
preventing those crazy impossible routes
Yes.
that might technically be shorter on the map,
Right.
but they don't make sense.
They don't make sense in the real world.
These models are ultimately designed
Yes.
to solve real-world problems
They are
with real-world solutions.
actionable solutions.
This has been really interesting.
It has
These optimization models can be applied to
I-
so many different things.
so many things.
Energy distribution,
Yeah.
pedestrian tours.
Right.
But as we wrap up,
Okay.
I want to leave our listener with something to think about.
Okay.
So we've seen how powerful these models can be,
Right.
finding the most efficient way to move things around,
Right.
whether it's electricity or tool lists.
Hmm.
But as these models get more common, more sophisticated,
Yeah.
don't we have to think about
Yes.
their limitations?
We do. They're not perfect.
Right.
They can't account for everything.
They're really good at finding the most efficient solution,
Mm-hmm.
given like a specific set of rules.
Right.
But they can't always handle the messiness of the real world.
They can't.
So like imagine a GPS. It
Yeah.
gives you the fastest route,
Right.
but it doesn't know about that unexpected road closure.
Exactly. Or that sudden traffic jam.
Right.
The model is working with the information it has,
Uh-huh.
but it can't predict everything.
Right. Like in that energy transportation problem,
Yes.
our model might find the best way to send the electricity
Right.
based on like the average demand.
Okay.
But what if there's a heat wave?
Yeah, what if everybody turns on their air conditioners
Yeah.
at the same time?
Suddenly we need way more energy than we thought.
Yeah. And then
We get a blackouts.
you get brownouts, blackouts.
The model didn't see that coming.
Didn't account for it.
So we have to be able to adjust.
That's right. Human oversight is key.
So it's not about just trusting the model.
No.
It's about using it as like a guide,
A starting point.
a starting point,
Yeah.
and then we can use our judgment
Yeah. You need that human
to
element.
handle those unexpected situations. It's like that balance
Yeah, finding that balance.
between what the algorithm tells us and what we know about the world.
That's right.
It's like a cookbook.
Yeah.
It gives you the recipe,
Uh.
but the real skill is adapting.
Adapting to what you have.
Yeah, to the ingredients and the situation.
Yeah.
But thinking about these limitations, it makes me think about the data
Yes.
that goes into these models.
Very important.
Garbage in, garbage out, right?
Yeah.
If the data is bad,
Yeah.
the model's going to give us bad answers.
It's not just about the fancy algorithms. It's about making sure the information is good.
Making sure it reflects the real world.
That's right.
Like, let's say we're trying to plan bus routes
Okay.
in a city,
Uh-huh.
and we only use data from people who drive cars.
Oh.
That's not going to work for people who take the bus.
That's going to create a system.
Not
That's not fair.
fair, not equitable.
Right.
We need data that represents everything.
You need good data.
And that's why we have to keep collecting data,
Yes.
analyzing it,
And making sure it's not biased.
to make sure these models are actually helping people,
That's right. It's an ongoing process.
like tending a garden. You can't just plant the seeds and walk away.
No, you got to take care of it.
Right, you have to nurture those plants, give them water,
Give them sunlight.
adjust things as they grow.
Yeah.
So our models are kind of like that.
They are.
They need care and attention.
They need to be maintained.
So as we finish up,
Okay.
the big takeaway is that these models aren't magic.
Yeah.
They're not going to solve every problem.
They're tools,
They're tools
powerful tools,
that can help us.
but we have to use them carefully.
Yeah, we need to think about them.
Right.
Make sure they're doing what we want.
That's right.
Thanks for joining us
It was a pleasure.
for this deep dive into network optimization models.
Fascinating stuff.
We encourage you to learn more.
Yes.
Check out the show notes
Uh-huh.
and keep exploring.
Until next time, stay curious.
And stay connected.
Yeah.